In this video, we are going to look at integrating power series. So let's start with this classic example where we're looking at, on the one hand, the function 1 over 1 minus x, which, as we've discussed, has this power series representation where it looks like the sum of terms from n equals 0 to infinity, x to the n. We start to write that out. That's 1 plus x squared plus x cubed, etc. This power series representation has the domain from -1 to 1, the open interval of radius 1 around the origin. What we would like to do now is anti-differentiate both sides. So I would like to create a new power series by term integration. So on the one hand, I'm going to say, what's the antiderivative of 1 over 1 minus x? And then on the right-hand side, we are going to go term by term, anti-differentiate each of these to form a new power series. Okay, so let's see what that looks like. The antiderivative of 1 over 1 minus x, that is -1 times natural log of 1 minus x. Okay, so that's the left-hand side when we anti-differentiate both sides of this equation. Now I'm going to say, and that I can say this is a theorem, I'll mention that again in a minute, but let's just move forwards with this act of integrating. What I would like to do is say, okay, on the one hand, I anti-differentiated this. Now let's go through and anti-differentiate the right-hand side. So 1 plus x squared plus x cubed dx. What I'm going to do here is say that this is an indefinite integral. So let me pick up a constant of integration. And because this is an infinite sum, I'm going to write the plus c first. So how about we write c plus, okay, so that's my constant of integration. Now let's go through term by term and anti-differentiate each of these expressions. The first one is x, then x squared over 2, then x cubed over 3, then x to the 4th over 4, and we continue in that way. We are going to put this in a power series form now, so I'm going to write sigma notation. Before we do that, let me figure out what to do with this leading constant of integration. If I set x equal to 0 on both sides of this equation, well, on the left-hand side, we'd be left with -1 times natural log of 1. So set x equal to 0, and we get negative natural log of 1 equals c plus everything else is 0. Natural log of 1 is 0, so this tells us that that leading constant of integration is just 0. Okay, so now that we've removed that ambiguous constant of integration, we can say that negative natural log of 1 minus x has this series expansion. Let me write it down in a condensed form as the sum. Let's see, we've got to talk about the indices in a second, but let's just look at what's going on here. We have x to the 1 power divided by 1 to make it look like the other terms, then x squared divided by 2, x cubed divided by 3. So it looks like x to the n divided by n. However, written this way, we can't have n equals 0. So we're starting when our first power is 1. So we are going to write this series as adding up from n equals 1 to infinity, x to the n divided by n. That's fine. I think this is a nice way to present this series. I just want to mention how you could re-index it so that you are starting from n equals 0. And there's a reason why I want to do this. So this looks better than what I'm about to write down, but just bear with me for a second. We could also take this very nice looking expression and re-index it, meaning shift where our lower index starts. I'm going to start from n equals 0 rather than n equals 1. The principle is if you lower this index by 1, you need to raise these by 1. So if I've lowered from n equals 1 to 0, I need to take these and bump them up by 1. So this is x to the n plus 1 divided by n plus 1. It doesn't look better, but the reason why I am mentioning this form is that if you compare it to what we started with, which was just x to the n, If I anti-differentiate the expression x to the n, I would get x to the n plus 1 divided by n plus 1 by the power rule, and that's what we see here. We're going to see more examples as well as a general statement of what we're doing when we integrate power series expressions. So we will have like a general form that we look for when we anti-differentiate a power series. So this form is nicer. We can say that natural log of 1 minus x, this function, without the negative in front, has a power series representation. How about we take the first form because it looks a little nicer, going from n equals 1 to infinity, negative x to the n divided by n. Okay, so we got this power series representation for natural log of 1 minus x through the act of anti-differentiation. Let's also figure out for this first example what the radius of convergence is. We'll use the ratio test for that. So for the radius, let's take the limit as n goes to infinity of this term with n equals n plus 1, or take the n plus 1 version. So negative x to the n plus 1 divided by n plus 1. Divide it by this expression with plain old n. That's going to be multiplying by the reciprocal, n over negative x to the n. As n goes to infinity, the ratio of n to n plus 1 goes to 1. This reduces to overall just the absolute value of x. For the ratio test, we want this to be less than 1. So that tells us that around our center at x equals 0, x can be between negative 1 and 1. So here the radius is 1. Okay, so that's how we can find the radius of convergence for this power series representation. Turns out it's the same as what we started with. So let me mention two theorems before we move on. And that is that if you have a known power series representation, like what we started with here, you can anti-differentiate term by term to get a new power series representation. So to get the power series representation for the antiderivative of the left-hand side, I just went through and anti-differentiated term by term the right-hand side. That we can do that is a theorem. It feels like it should obviously be true, but what we're really saying is the integral of a sum is the sum of the individual integrals. So that's actually a statement that would need to be shown, and we don't show it in this look at calculus. So that's one theorem, that we can do this term by term anti-differentiation. And the other one is that the radius of convergence will be preserved. So in future examples, if we integrate a power series, we will not need to do the ratio test if we already know what the starting radius of convergence is, because we'll keep the same radius. Okay, let's look at this exercise, which is actually going to give us one of the reasons why we use power series. So this is part of the motivation behind ever writing down a power series representation for a function. What we're going to do is take the function that we were just looking at, natural log of 1 minus x, and anti-differentiate the product of that function with x to the 6th. So you can look at this and you can try to anti-differentiate it, right? But it's not going to be something that we want to do by hand. So instead of writing down a closed form expression for the antiderivative of this in terms of what you could call elementary functions, let's take this integrand, replace it with a power series representation. So the first thing I want to do is write down a power series representation for x to the 6th times natural log of 1 minus x. That will be inside of the action of this integral. We can then integrate term by term, and then with that antiderivative, write down a new power series representation, which represents the antiderivative or the family of antiderivatives for x to the 6th times natural log of 1 minus x. Okay, we've done most of the work on the previous exercise. So we already have the power series representation that we need for natural log of 1 minus x. So let's move forwards now and say that this integral could be thought of as the integral of x to the 6th times a power series representation, and I will take the n equals 1 version because it looks a little cleaner. So indexing from n equals 1 to infinity, negative x to the n over n dx. So I took the function natural log of 1 minus x, which is hard to work with, and I've replaced it with its power series representation. This is valid on the domain from -1 to 1. So keep that in mind. We will talk about the radius of convergence for this operation that we're doing at the end. Okay, we're going to need to do some anti-differentiation, but before we do that, let's bring the x to the sixth inside of the sum. I'm also going to take the negative and just pull it in front of everything. So we have -1 times the integral of a sum from n equals 1 to infinity, x to the n plus 6 divided by n dx. We could actually anti-differentiate this expression and skip expanding it out term by term. But since we're new to this, let me write out the first few terms of this, and we will anti-differentiate one at a time, collect them into a power series, and then compare the final result with what you might think of as the antiderivative of this term. Okay, so let's expand this out. We're going to say that this is -1 times the integral of, okay, we're starting with n equals 1. So if I start writing out this sum, the first one is going to be x to the 7 divided by 1. Then the next one would be n equals 2, so we'll have x to the 8 divided by 2 plus x to the 9 divided by 3. And I think that will be enough. Let's now do some anti-differentiation. And as we mentioned on the previous example, we're doing an indefinite integral. So let's pick up a constant of integration and let's actually write it first. So how about c for constant of integration minus what will now be term by term anti-differentiation of the expression in this integrand. Okay, so let's anti-differentiate x to the 7th, and we will get x to the 8th divided by 8. Then we'll have x to the 9th divided by 2 times 9. Then x to the 10th divided by 3 times 10. You'll notice that I did not write out 18 and 30 for the denominators, and that's something that I actually recommend doing in general with sequences and series. If you think that you're going to look for a pattern and you want to try to describe something in terms of an index n, sometimes it's easier to see if you leave terms that you're combining like written as a product like this. So I might be able to see a pattern for 2 and 3 versus 9 and 10 more easily than I would see a pattern with 18 and 30. Okay. This is not too hard to do anyway, because we know what the goal is. Ultimately, it's going to be an antiderivative of this expression. So we'll have c minus, and then I want to write this expansion out as a series. Given that these powers are so high, there are different ways that we could do this, but I think what I'm going to choose to highlight is this 2 and this 3 in the denominator, because that looks like the indexing 1, 2, 3. We could even add a 1 times 8 to the first denominator. So I look at the 1, 2, 3, we think maybe that's n equals 1, 2, 3. Okay, so we'll have n, we'll be starting with n equals 1 for this term, going off to infinity. And then this is 7 higher than that, that's 7 higher than that, that's 7 higher than that. So it's going to be x to the n plus 7. Whoops, I wrote n plus 6, but I said 7. X to the n plus 7. And then this number up here matches this other term in the denominator. So n plus 7. Okay. So the general family of antiderivatives for the function, which can be written as the product of x to the 6 times natural log of 1 minus x, has this power series representation. Here, I'm not going to specify any constant of integration, because I'm actually saying if you anti-differentiate this in general as an indefinite integral, it's going to pick up a constant of integration. So we have infinitely many antiderivatives kind of differing by constant. So we'll leave that constant out front. And then this is the kind of the power series part. If you look at the terms that we have here and compare them to what we started with before we anti-differentiated, we're anti-differentiating with respect to x. If you do the power rule on this expression, well, n is just a constant. Again, x is the variable we're anti-differentiating with respect to. Using the power rule, you would take this exponent, bump it up by 1, and then divide out by that. And that's exactly what we ended up with here. I don't know if you can see. Let me write it a little bit larger. C minus the sum from n equals 1 to infinity, x to the n plus 7 divided by n times n plus 7. Okay. So this n plus 6 went up 1 to n plus 7, then we divide out by that. So if you differentiate this expression, you should get back to this one. That's not an accident, right? So that's how this works with these power series antiderivatives. Okay, so while this is something very hard to anti-differentiate, we can pass to a different kind of problem. We can say, take this integrand. If you can give it a power series representation, then you can do the antiderivative of that power series representation, which is something that's going to be easier to do. We end up by able to say that the antiderivatives for this expression have this power series representation. In the next exercise, what we're going to do is use this kind of approach to estimate a definite integral. Actually, before we move on, I forgot to mention the radius of convergence. When we anti-differentiate one power series to get to another, we keep the same radius of convergence. So going back to the power series that we brought in, this was the power series for natural log of 1 minus x. We knew that this had a radius of 1. So this one will have the same radius of convergence. So our computation here is centered at the origin with radius 1. In this exercise, we would like to approximate the definite integral of 1 over 1 plus x to the 5th integrated from 0 to 1/2. Now, there's more going on in this problem than what we saw in the last example, including this approximating it to 3 decimal places. Before we get to what's new, let's focus on what we already know how to do. And that is, we have this integrand here, 1 over 1 plus x to the 5th, which looks like our prototype 1 over 1 minus x. Needs some adjustment, but it's going to be able to follow that mold. What I would like for you to do is take this integral and make the adjustment necessary on the integrand so that we can bring in a power series representation. So go ahead and first do that step. Then do the anti-differentiation. You can try to stick with the power series representation and then just anti-differentiate the expression, or you can write out the first few terms, term by term, anti-differentiate, and then collect into a power series representation. So you can anti-differentiate however you like, or you can do it both ways and see if you get the same thing. If you'd like to, you could then proceed to plug in the top and bottom bounds, but that's where the material is new. So I would like for you to pause and work out the conversion of the integrand to a power series and then the anti-differentiation. Then we will evaluate the power series at the top and bottom bounds to the best of our abilities, and then I'll talk through this estimation process. Okay, the first thing to do are the steps which are familiar. So let's take the integrand and write this first as 1 over 1 minus negative x to the 5th dx. Now I'm going to use our known geometric series looking power series representation for this function. So that's going to be the integral of the series index from n equals 0 to infinity, negative x to the 5th to the n dx. Let me clean this up a bit. Oh, also, I forgot that we are doing a definite integral, so I'll bring in the top and bottom bounds. We are going to be doing the integral from 0 to 1/2 of the series now from n equals 0 to infinity, negative 1 to the n, x to the 5n. Okay, I secretly hope that you did both, that you both anti-differentiated this as it's given and you wrote out the first few terms and kind of compared what happened. I'm just going to anti-differentiate this now using the power rule. So we will say that to do this antiderivative is to take the series from n equals 0 to infinity, negative 1 to the n, x to the 5n plus 1 divided by 5n plus 1. This is a definite integral, so rather than a constant of integration, we're going to have evaluation at the lower bound of 0 and the upper bound of 1/2. Okay, so hopefully this part was comfortable. Now let's see what happens if we plug in our top and bottom bounds. We're going to evaluate this just like we usually do with definite integrals. When I plug in the top bound of x equals 1/2, what we'll have is the sum from n equals 0 to infinity of, I'm going to rearrange this a little bit so that it looks like negative 1 to the 5th divided by 5n plus 1 times 1/2 to the 5n plus 1. Okay, that's what happens when we plug in the top bound. And then if I plug in x equals 0, every single term in this power series expansion has an x in it. So when we plug in x equals 0, it all gets wiped out. Okay, to make sure that our evaluation here was valid, that it was an okay thing to do to plug in x equals 1/2 and x equals 0, let's make sure that we're working within the domain of convergence. Our power series here is centered at x equals 0, but what's the radius of convergence? For that, we want to figure out what the radius of convergence for the series that we anti-differentiated in order to get to this one was. I think the easiest form of it is to look back here at the first conversion to a power series that we did. So this series is based on the geometric series approach, which means that we need this base, negative x to the 5th, to be less than 1. In other words, x to the 5th needs to be between negative 1 and 1, so the radius here is 1. Since 1/2 is within the interval from negative 1 to 1, we're good. So this computation is valid, so we can continue on. Now, looking at what we left off with, half of the computation went away when we plugged in x equals 0, so we're left with this convergent sum of numbers. So the question is, looking at this sum of numbers, can we estimate, correct with the first 3 decimal places, what this would add up to? So I'd like to approximate this sum where I know my first 3 decimal places are correct. Then it's like, okay, when did we know that we could estimate, when did we have remainder theorems, things like that? Here, what you want to focus on is the fact that this is an alternating series, and we have a remainder estimate for alternating series. So look at the alternating series remainder. What we said was that if you take a partial sum for a convergent alternating series, then the size of the error, the distance between your partial sum and the true sum of the series, the size is less than or equal to just the size of the next term without sign that you would add up. So let me write that down. How about I just write error? The size of the error is less than or equal to the next term, a n plus 1. So we want to figure out how many terms we need in order to say, hey, the next term is really small. It's not going to affect the first 3 decimals. Okay, let's see what the first few look like. So a sub 0, we're starting with an index of 0, is going to be negative 1 to the 0 over 1, 1/2 to the 1. So it's just 1/2. And it might be easier to work in decimals, so 0.5. The next term that we would add to this happens when n equals 1. So for that, actually, I shouldn't be using the negative 1. That's the alternating part of the alternating series. We're really looking at everything else for these terms here. So the next term would be 1 over 6 times 1/2 to the 6th. That's already pretty small. I wrote it down as a decimal, and what I wrote down, assuming that I crunched this correctly earlier, was 0.002604. Just write down enough decimals so that we feel good about the first 3. The next term that we would add up happens when n equals 2. And that term is going to look like 1 over 11 times 1 over 2 to the 11. This is obviously even smaller, and it's going to be 0.0000. So the first 4 decimals are 0, then we have 4, 4, etc. Okay, were I to start adding up a partial sum, what we could notice is a sub 0 plus, sorry, first term is positive, the second term is negative. A sub 0 minus a sub 1, that would be the sum of the first 2 terms, here and here, together with a sub 0 minus a1 plus a2. If I added up the first 3 terms in this expansion, they have the same leading 3 decimals. In other words, this plus a2 did not affect the first 3 decimals after doing the sum of the first 2 terms. And then a3 and on is even smaller. So if anything, I'm just going to have more and more zeros here. So if I just add up really the first 2 terms, we get the sum correct with the first 3 decimals. And if you do that, you get 0.497. So let me do approximately 0.497 . Okay, so that estimate, just recall the alternating series remainder estimates that we did a while ago. So if you recognize that your power series is an alternating series, what we see here in the numerator, then you can use the alternating series test and the alternating series remainder to approximate it to a certain number of decimals. Let's summarize the main ideas that we saw in this video. Suppose you have a function f of x with a known power series representation with some positive radius of convergence. Then we can anti-differentiate both sides of this equality to get a new function, the antiderivative of f, with a new power series representation. What that will look like is the antiderivative of f of x dx is going to be ultimately the term-by-term antiderivative of the power series. So you could anti-differentiate this, this, this. If I'm just doing an indefinite integral, first thing I want to do is pick up a constant of integration. So we can say that this is c plus term-by-term anti-differentiation, which you can actually do by looking at your series notation and say that this is going to be the series from n equals 0 to infinity. Cn, the original constants, x minus a to the n plus 1 by the power rule, and then divide everything by n plus 1. Okay, so that would be the power series representation for the antiderivative of f. And as is always the case when you're talking about general antiderivatives, we have a family differing by constants. The radius of convergence is the same. Okay, that wraps up this lesson. I want to mention 2 kind of distinct viewpoints that we saw in the exercises in today's lesson. On the one hand, we could anti-differentiate f with our first example to get to a new closed form expression. In that first example, we were able to use this methodology to write down a power series representation for the function natural log of 1 minus x. So that's one application, is to say, hey, I know what this antiderivative is. It's a function that I know, and here's a power series representation for that function. But then the other examples we saw, what we were actually looking at doing was really an application of power series. We had an integral that we couldn't easily do. So it's like, how do we work with an integral that we can't anti-differentiate by hand? Here is one way to handle such a situation. So if you can take your integrand, f in this case, and say, hey, I don't know what the antiderivative for this is, but I do know a power series representation, then you can anti-differentiate that power series representation to produce a power series representation for the integral that you don't know by hand. So there were kind of 2 ways to see this occur. One is to come up with a power series representation for a function we know, and the other one was to come up with a power series representation for a function that we don't know.